All right. Is this on? No. Better? Well, not really, you say. Well, let me start anyway. And it's working. Okay, good. Okay. So I left off yesterday. I've just started introducing a scalar field on some curved background manifold. I'm going to assume that I can foliate the manifold with a family of Cauchy surfaces and choose local coordinates where x is coordinates for the sigma and x0 labels the member of the family. Is basically going to be our time coordinate, local time coordinate. Now, if you vary this equation, you get the Klein-Gordon equation, which I wrote down yesterday. And then an important ingredient in what we're going to talk about here is the Klein-Gordon norm. So or inner product actually. So let me define that for you. Basically, if you have two complex valued functions, f and g, then their Klein-Gordon inner product is an integral over sigma of a current j mu, which is a function of f and g, where the measure is constructed from the induced metric, and so basically it involves the embedding. So this is so this is as before. This was the induced metric here, and this is a future-directed unit normal to the Cauchy surface. Okay, and then the current is given by the following expression. There's a minus I out front, and then I have f d mu of g. So I have to take the complex conjugate here. And this is, of course, just very much just in parallel with what you would do if you were doing Klein-Gordon field theory on Minkowski spacetime. And and the reason this is called a Klein-Gordon norm is because if you actually ask, if you use the Klein-Gordon equation, you will see that it actually implies that this current is conserved. So that's easily checked. And it follows immediately from that this inner product is conserved as I evolve from along my Cauchy surfaces. So if I have evaluated it on some surface sigma 1, it'll actually be the same at all the other surfaces. And so basically this is fairly straightforward. We have here sigma 1, then there is our time variable x0, here's my sigma 2, and then I basically all I need to do is to use this. This holds everywhere, and then you apply Gauss' law in this region. And then you will find that that tells you that these inner products are the same. Okay. Now, you can easily establish, and I recommend that you do, convince yourselves of this, that there are some elementary properties that this inner product has. So if I take So this assigns a complex number to a pair of functions. If I take the complex conjugate of that number, I will get negative. So this is a simple exercise. And of course, if I reverse the order of G and F, I get the complex conjugate. And that is,
Sorry?
yes.
F and G are function of the scalar field?
No, they're any function on the manifold, right?
Okay, and then we should use the Klein-Gordon equation for what? For the scalar field in order to...
Yeah, sure, these are going to be, if this is satisfied. So what I'm going to apply this mainly for is I'm going to do a mode expansion of the scalar field.
Okay.
And so those are they form a basis of functions on the manifold. And so I will work with solutions of I'll write things in terms of, I can take any function I like and I can spend it in modes of the field and use these properties. So I'm using the Klein-Gordon equation to establish this. This is, on the other hand, is just these are just come from the definition. Okay. And so, and oh yeah, of course, this also implies that must be equal to 0. Okay. And an important thing to note here is that this inner product is not positive definite. Okay. Now, and as I said, what I'm going to do is to write the field in terms of a complete set of orthonormal modes. And I'm going to label them with I. This, of course, can also be a continuous index. I have some coefficients. Okay. And then my orthonormality relations are the following. And again, you can check this from, and then they will, right, okay. And then of course, you can use these relations to express the mode coefficients as inner products of a given mode with the field, usual way. And then we are going to basically carry out canonical quantization by promoting these coefficients to operators and work out their commutation relations. So that will give us, as usual, that these are creation and annihilation operators for field modes. So far, we could have been working on Minkowski space. We've not done anything that's different. What we will find, and we'll continue, so we have a vacuum state. Once we have carried out a mode expansion like this, we've got these commutation relations. We will build our states by identifying the vacuum state as one that's annihilated by all the positive frequency modes here. That's what we will, and then we will form a Fock-space representation. So the vacuum state satisfies for all I, and we have a Fock-based basis. That's A1 and 1 acting on this vacuum. So this is just a standard construction. If I'm doing this in Minkowski spacetime, it's easily, these mode functions are easily worked out. Otherwise, if you're on a curved background manifold, of course, you have to solve the Klein-Gordon equation on your particular space. Yes?
In the correct expression of UA and VJ, will there be a Dirac delta function because UA and VJ are both?
Well, as I said, this is shorthand. If it's a Dirac delta function, if it's a continuous index, if not, no. So this is it's an avatar of a Dirac delta function if when appropriate. Sometimes you can have a countable basis as well, depending on the manifold you're working on. Okay. But in Minkowski spacetime, of course, I do, of course, have plane waves. So this is when M is simply R cross R3, right? Which I'll write R13. Okay. And then my UK are labeled by a three-dimensional vector. Now there's a normalization coefficient here that comes from, that normalization condition up there. Right, and there's an I here. And the omega dispersion relation is simply right. And I'm going to define my omega to be, I'm going to pick the positive root here. And so so this is my positive frequency mode, and then its complex conjugate is the one you get for the corresponding negative omega. Okay? Now, in this case, we have symmetries. In particular, we have time translation symmetry, and we have spatial translations. These generate symmetries. And those symmetries are, of course, just a subset of the Poincare transformations. But it's important that for Minkowski space, they leave this vacuum invariant. So if you've solved your Klein-Gordon equation in one set of coordinates in one inertial frame, if you like, in Minkowski space, you can carry out an arbitrary Lorentz transformation, and you will find that, sure, you'll get another mode expansion in the new coordinates, but that you will find out that the annihilation operators in the new basis will actually annihilate the same vacuum. This is an important property of Klein-Gordon field in Minkowski. Now, this is, of course, not going to hold in general because we do not have, on an arbitrary curved manifold, you do not have Poincare symmetry. So, and that is going to be the main, so that's the difference that is going to, we will see in the particular case of a scalar field on a background, black hole background. We will see that that has important consequences. Okay. Okay. So if I'm on a general background, I do not have these symmetries, and then different choices of coordinates will lead to inequivalent. So you will not, they will give you a different vacuum, and then when you do the usual construction, you will build basically an inequivalent representation of your field. Okay, so if we have a curved background, there are no symmetries. Now, of course, we're going to assume that we will continue to have spherical symmetry in our case, but that's not, of course, in general, that's not going to be the case. And so no preferred coordinates either. So basically, using inertial frames in Minkowski space is preferred. That and that's, of course, is an obvious choice when you're working. Now we will see, of course, that there exist other coordinates. When we talk about the Unruh effect, when we have accelerated observers, and of course, then there are other coordinates that we're going to use that are non-inertial, and then we'll see very similar effects to as what we will see for the black hole background. So the two are closely related. But let's look at the black hole case first. So what this means is that what you mean by positive frequency is not unique. And so imagine that we're using a different set of orthonormal modes. Let's call them UI twiddle, okay? And they're, of course, still functions of the position on the manifold. Then we can still we can, of course, expand our field again. And now we're going to have a sum over new set of annihilation and creation operators in exactly the same way. Okay? And then we have a new vacuum, which is defined by the new annihilation operators. Let's call that vacuum 0 tilde. So I proceed exactly in parallel, but this defines a new vacuum and a new Fox-based basis, right? So, but I'm doing a linear field theory, so it's a free Klein-Gordon field. So these two representations should be linear, should be linearly related. Okay, so that's, and the transformation that takes you between these inequivalent bases is called the Bogoliubov transformation. Okay, so that's. Now we'll see how this works out concretely when we do the black hole background. So I'm just doing this kind of formally here.
Sorry.
Yes. Yes.
The fact that the positive frequency modes are not unique is
it's not completely clear to me what is related to curvature of space-time. In this sense, maybe this is my understanding. You could, even in the Minkowski case, do like a change of basis, let's say, for the creation and inflation operators. But in that case, they create the anihilators and create the same vacuum. Right?
If you do a Lorentz transformation, yes.
Okay.
If you go from one inertial frame to another,
Okay.
then that's the case. If you go, if you go to so-called Rindler coordinates, for example, which are natural for a uniformly accelerated observer, that will no longer be the case.
Inertial case. Okay.
Okay. Yep.
I couldn't understand what is the rationale for saying that these two bases are related linearly?
Well, these guys are, of course, going to be solutions also of the Klein-Gordon equation, right? And then I can use my inner product, for the modes, and just I could write this one as it's two ways of writing this as linear combinations of functions, and then of course, these Bogolyubov coefficients are going to be given by the inner products between the modes in the different representations. So we call those overlap integrals, and that's exactly what we'll have to calculate when we want to figure out the spectrum of Hawking radiation. Okay. So maybe the best way to do it is you simply write down ui as a linear combination. So if you like, this is just a definition of these coefficients. So, yeah. And then I have beta ij. And what I'm saying here is that beta ij is equal to 0 if ui and uj are related by Lorentz transformation in flat spacetime. Okay? Then positive frequency modes, they can be linear combinations of other positive frequency modes, but the negative frequency modes don't come into it there. And that's simply a statement. Sure. You raised your hand.
Yeah. Scalar is real.
Say again?
Scalar is real.
I'm working with a real scalar, yes.
So why u star I is not equal to u minus I?
Oh, well, it's the usual thing. You can always take a real field. You will, impose a reality condition at the end. It's just saying that, just as I can, I can Fourier expand in, and this is just, in flat space-time, this would just be Fourier mode expansion in Fourier modes.
I don't understand. The sum is over only positive I?
I mean, you can take a real valued function and you can write it as an integral. You can always do this. If you're just working in three-dimensional space, you can take an arbitrary function and say that it's d3k. It just means if this is real value, that's a condition on your Fourier coefficients. That's all. Okay.
So there is a connection between different modes, different positive and negative modes.
Right. Sure. Yeah. I mean, the condition is on the field overall, but you're allowed to use. Okay. So what I'm using simply is that the UI, by assumption, form an orthonormal basis for my field space, right? And that means that I can take any function on that space and I can write it as a linear combination of those modes, right? And then in particular, I can take one of the other modes that is a function on that same space, and I can write it as a linear combination. So that's all I'm doing here. Just using that these guys are form an orthonormal basis. All right? And then, of course, I can now leave this as an exercise for you. You can check that your alpha ij are then simply given by, like so, and your beta ij are actually minus. And this just comes from the way the inner product, the sign conventions in the inner product. Okay. And also, you will also see that I can do a corresponding then expansion of my mode coefficients. Ji. You should check this as well. Okay, because this is something we're going to use later on. Okay. So the annihilation operator in my original vacuum is going to be a linear combination of both annihilation operators and creation operators in the other vacuum. This means that if I have that let's say the original vacuum then is actually, when you apply these operators to it, it will be clearly, it is not a vacuum state in the other representation unless beta here is non-vanishing. So if the beta coefficients ij are not non-vanishing, then what we can say is that ai acting on the other vacuum is not going to be 0, right? Because if I act on these guys, will all annihilate this one, but these guys will not, right? And this will tell me, I can write this out as I can ask what is the occupation number of a given mode in this other vacuum. And that's going to be given by sum over j beta ij squared. Okay, so if you calculate the Bogoliubov coefficients, then you can say, well, in my tilde vacuum, I can ask what is the occupation number of the ith mode of the original vacuum, right? The original Fock space basis, and it's going to be given by this expression here. And to calculate this guy, we have to basically calculate this inner product. So if we can do that for our setup, then we will be able to answer the question, what are the modes that are with respect to this vacuum that are, in this vacuum, what are the modes with respect to the other vacuum that are going to be there? Okay, so let's see how this works for a black hole. And this is exactly the computation. I'm basically following the computation that Hawking did in his original paper. There are some additional bells and whistles that he discussed in his paper, and it is it is a beautiful paper. You should really look at it. His Communications in Mathematical Physics in 1975, I believe it was. Okay. So, what's the setup then? The setup then is we have a background geometry where we form a black hole. Remember, we've drawn this as follows. So early on, so we have some collapsing matter here, or we Actually, we're going to look at a slightly simpler model in a minute. So here's my black hole region. Now, the setup is, and the assumption that Hawking makes, is that his scalar field is in its vacuum state here at very early times before the black hole is formed. So basically, there should be no incoming scalar field radiation from out there. And, that's a reasonable starting point, right? So, and then back here, the vacuum he wants to. So of course, this is asymptotically flat spacetime. So if you go to a sufficiently early slice here, you're going to basically be doing standard Minkowski. Your modes are going to reduce to those of the Minkowski plane waves back here, right? Same is going to be true out here when you're far away from the black hole, right? So that is certainly a simplification here. But you then have to think about the propagation through the background spacetime, which is where the interesting bit comes. So I'm going to define the vacuum down here as the one that's annihilated by the A twiddles. So here I have my, and I'm going to work in this vacuum so that there are no excitations, no field excitations coming in from the past here. And then my other modes are going to be out here, right? Now, an interesting thing to note, and this is going to be crucial to the effect, is that when I think about a mode up here, it's coming from somewhere. Well, there'll be an outgoing mode here that's coming out, and it'll have come from down here somewhere, right? And then it will presumably have, perhaps interacted with the star down here and or whatever matter there is, and we're going to leave that aside for the moment. But what is very clear is that there are not going to be any modes that are coming from. So basically, any modes that you're going to find that you take your mode, we're going to reflect them off the origin here. They're going to come back out, and so it's only this part here that's going to have support in this integral that we're going to do. We'll see that in a minute, okay? And this is why there's going to be a mismatch, a very strong mismatch between the modes that I get from evolving. So whatever functions over here that will evolve into my modes over here are quite different from the modes mode expansion down here. Okay. So we're going to assume that our scalar field is this state for and for simplicity, I'm going to take this to be a massless field, so it propagates along no lines. That's simply a matter of convenience. And what we want to do is calculate this Bogoliubov coefficient that was minus all right. And the way we're going to do that is we're going to evolve the UI mode back from scribe plus, so that's up here, using the Klein-Gordon equation, of course. And until we get to xi minus. And we'll use some Dirichlet condition or something at r equal to 0. And then if this line here, remember if I'm using the u and v coordinates that were appropriate to the null combinations of coordinates in Minkowski space here, this will be what you call v equals b. It's some function I'm going to call, some constant that I'm going to call b. This mode then will only have support 1 little b less than b. Okay. And what we'll see is that the main contribution to this overlap integral, which is what this is called, comes from very close to the horizon. So it comes from v getting very close to b. Okay. So the modes that actually get reflected very close to B are exactly the modes that are extremely close to the horizon up here, coming back in this computation. Okay. Now, that should already be a little bit worrisome for us, because those modes actually have been redshifted from an enormously high energy down here. If you really go wait long enough, they have been, these are modes then that are starting extremely close to the horizon, and then they will be redshifted. So what you have, or another way to say it is that when you evolve a mode backwards, it gets enormously blue shifted. And Hawking simply said, well, this is true, but we're actually going to use it to our advantage. We're going to assume these are extremely high energy modes that will then, this matter that's forming the star will be completely transparent to them. They'll just go through it. He uses ray tracing, basically uses geometric optics to get his answer. People worried about that, of course, at the time. And it turns out he gets the right answer this way. And there are other ways to do the computation that I'll talk about later, where you actually avoid ever having to talk about such high energy modes and you get the same answer. So I'm just telling you that. I'm going to follow this original calculation because it's simple and it's easy to follow conceptually, but and the important thing that you get through this is that when you go extremely close here, up here, which is late times outside the black hole, remember the Penrose diagram is a little bit tricky. There's the conformal transformation. There's really an infinite volume up here in the corner. But you get this universal behavior at very late times that will give us the thermal spectrum. Okay. And now to simplify things a little bit, we're going to actually, rather than think about a general collapse here, we're going to think about a simple model where we just have a null shell that comes in and collapses so that we have basically vacuum, Minkowski spacetime on the inside, and then the shell comes by, and once it's passed, you have Schwarzschild solution on the outside. This is basically, we're appealing to Birkhoff's theorem here in GR to tell us this, that once the shell is inside you, what you have outside is just the Schwarzschild metric. So we're going to patch together the Schwarzschild metric and the Minkowski metric on the inside through the shell. And this can be done using some junction conditions that are well known in GR. And we're actually not going to worry so much about those conditions. We don't need that. What we will need simply is these two parts of the geometry that. So this is a model that's discussed in the book by Birrell and Davies. And I'm sort of following that computation, not at least sort of, we're largely doing that calculation here with the little bit, slight differences. Okay. Okay. So then what we have is it's pretty much the same diagram, except now I'm not really thinking about this as a bunch of matter. I'm just thinking about the surface of the shell. So the shell is doing whatever it does here. So this is the shell surface. This means that I have Schwarzschild out here. And I have Minkowski in here. Okay? And the procedure now is, first of all, I solve the Klein-Gordon equation. Both outside and inside the shell. Okay? I'm going to match the solutions across the shell. I'm going to evaluate the overlap integral. So that's the okay. So this, I need the metrics, right? So let's start with the, I guess I have some more space there. So we need to establish some notation here for our metrics. So the inside metric I'm going to write in no coordinates. It's a Minkowski spacetime, so I just write it like this. I'm going to use capital letters for the coordinates inside. And of course, I'm doing this in asymptotically flat thing with my horizon is going to have the topology of a sphere here. I'm not doing a planar black hole. I'm doing just a usual Schwarzschild black hole. All right. And I'm going to adjust my coordinates in the following way. So the capital V here is a time coordinate on the inside plus a radial coordinate r, which I'm going to choose as the thing that determines the area. This is basically a coordinate choice, but I'm going to choose it so that the origin of coordinates is sitting on the shell surface. This I'm allowed to do. I can always just minus r plus r0. Okay, so I'm just taking my radial coordinate and I'm adjusting it so that it is actually 0 at a particular point on the shell. Okay, so it'll be something like here. So I'll have my origin of coordinates here somewhere. Okay. Let me pick it to be here. So that's something that I can do, right? Yep.
R0 is a constant initial.
R0 is just an arbitrary choice that I make. It's I've decided I ask where is the shell at this point. This will be r equal to capital R0. That means that my VU coordinates refer to that location as instead of, normally when I defined them, I would have used this as my reference. Instead, I'm just choosing this point as the reference. And the point is that I'm going to do that also. This is a point that's common to the outside solution and the inside solution. So I'm going to make the same choice. So the origin is in the same place for both of them. That's all. All right. Okay, so how about the outside metric? Well, there I'm going to have different coordinates, of course. I'm going to have minus f of r dv du. These are the now lower. These are the remember I formed the torus coordinate, and then these are the null combinations of outside t, and okay, so, well, let me finish writing this out here. Okay, and here now, lowercase v is going to be my coordinate, asymptotic coordinate, so Schwarzschild time coordinate, plus the torus coordinate minus R0 star, lowercase u is t minus, okay, and then I'll remind you simply that so basically this so the relations between R0 star and R0 are the same as what we had for the, so this is just the, okay? And I'm doing this somewhere out here where my R is, I'm going to patch this at a radius before it passes through its own Schwarzschild, its own event horizon, which means, right, okay? And of course, the same thing goes for R star. It's just the usual. Torus coordinate. So this is the torus coordinate that corresponds to R0 that we had here. And then if we do that, then we can actually go back to this diagram and see what I've done now is to arrange for, it's probably best if I draw this again. Here's my shell. Let's say I do this over here, okay? Then basically what I'm saying, remember, outside here, this is now the v coordinate, right? So I'm arranging things so that this here is v equal to 0, I believe. Yep. And this is going to be u equal to 0. And then inside, this is actually capital V equal to 0 and capital U equal to 0. That's the point of this shift here. Right. So the origin of both my null coordinate systems is picked at some arbitrary point that's sitting on the shell. Okay, it's not something that I had to do, but it's convenient, okay? So furthermore, we know in this coordinate system over here that as I go towards here, this is u goes to infinity, right? Remember, this point we had already said was going to be v equal to b, right? That's simply we're defining b as whatever is this point. And here, what I'll find is that this curve here is u equals some constant u0 that is to be determined. Okay. So constant capital U is always curves like this. Constant capital V are curves like this inside the shell. And the same goes for the lowercase letters on the outside. So I'm patching together these solutions. I'm simply adjusting my origin so that they... All right. So basically tau equal to 0, which is the time variable on the inside, r equals to r0. This corresponds to and also. Okay, so this. So is this fairly clear? What these are? All I'm doing here is just establishing coordinates for these two. And of course, I'm also using the fact that I have a Schwarzschild solution on the outside and I have a flat spacetime on the inside. Okay, I guess let's take a 5-minute break until 10 o'clock, right? We're about halfway through the hour. Then I will carry out step number 1 here, 2, and 3. All right.
Si intende proprio un filo, cioè è continue
And then that's when you would then compare. You have to have the nodes in the same proportion surface to be able to calculate.
Excuse me, I think I'm still confused.
Okay.
I didn't understand the answer. I don't understand how you define a vector because you say that AI and relates that if there is connection between AI and AI, that AI
Well,
how do you
right. So I have basically, what you see here is I will find plane wave solutions up here. And then we can say, out here I am asymptotic to flat spacetime, it's basically the Gaussian. And I'm choosing actually coordinates that f will go to 1 asymptotically. So it really literally is the Gaussian spacetime. And then once I have, and then I will define my, okay, I'm basically using wave solutions. I'm going to put n to 0 just to make that a little bit easier. So then omega is going to be, yeah, and I'm going to have a radial momentum, which, once I do this, I have to, of course, I'm going to solve this in spherical harmonics. I have to expand them in spherical harmonics, and then I have to solve the radial. The radial function will have a k number, and that is going to be, as I go further and further away, that is going to be this. There's a simplification. Especially, yeah, so that then I would say e to the minus r plus I omega is negative frequency, but I'm if it's minus I omega, it's a negative, it's positive. then I will define, go through my usual Kasky measure, Kasky space. I will tell you that you take the mode coefficients of the positive relation operators. So you do that. You do the same thing down here. Now you might say, okay, this is also a specified. It turns out that's not because in order to relate these are actually not the related because of the diagram. These are actually things that came from the past. And these are things that are going on. And so in between we have that's what we're trying to figure out. I'm saying that the law so that and we will find that is actually a very complicated function.
I get that, like, we're trying to get all that. Because in practice, it's always out of the whole science here. So we have freedom to choose this to be any we have freedom to choose this point to be any
Yeah, but I think
Right,
those
this
days.
has to be Charles.
No, this is the normal. This is going to work. That's a definition of architecture. What I mean, I will do exactly the same kind of mode expansion except these are equal modes. They're going to be functions of the last best field, it means I have functions of t plus r here, functions of t minus r here, but then y or I'll do exactly the same construction. It's just that, and look, this is not the reason why I haven't got things is
squares.
Okay, we still haven't found that. Okay, I see. Okay,
that is the problem.
thank you.
But like usually in the argument,
Well, I'm going to tell you. That's when I solve the equation. I'm going to solve the equation. Solve the equation.
yeah, I guess if you want to
And then there's hash. Because you will see that this is exactly where it is. Here, the modes are interested in the modes of the square waves, actually regular spherical waves coming in. Here, the modes that are spherical waves coming in. And it's trying to compare. Ask what is the function that gives rise to our coordinates. Figure that out. And then I'm going to calculate this overlap. Actually, it's going to go up. Find the data coefficient is actually lost. Well, that's I guess I just erased it. What it means is that if you have this non-linear data coefficient, then it tells you that the state of the theory, which is the vacuum where there are no characteristics, is actually something which is not that is the state that you have of the theory, which of course once you look carefully,
I'm just noting who's going to
what is here, the mode forward is actually not going to be mode to the vacuum. This is the state that
I don't know. So I got the very desperate email the other day. Like last call.
this is not
they're kind of discouraging us.
this is actually they actually, yeah, they must
Of the people who are not from Durham, a decent chunk of them went to Durham before. There's at least 3 of us who are like just going back. I think we could go back to Durham for a couple of days. Get free accommodation. That's part of the conference. it's free from liquid. Yeah, it's part of the reason I love going like that. I just go like, why don't you have to get much information in the train?
So something that came at the speed of light here. Basically, in order for something to come from up here, something here will have to reflect off here, or it will have to go faster than the speed of
Oh, yes.
there I'm using this. This is how I describe customization. Then the other one is
I like it, but I'm sort of trying to be very, very abstract. So I like it. I can't execute that. I don't practice like literally the goal I know like repeat yes. Yeah, okay, so keep the white thinking just now. But it just like takes it. Yeah, like I can't like round it. Like I like it because I've done 18 pages of it. I don't know what you answered to tell me. Maybe I'll do some 18 pages through. I think I love that with the table of contents. I've opened it once. Oh, the tablet. I've put like 4 years. I used to have one down have sword broken. Like our button
Can you maybe say what is the foliation you chose? What is the foliation you chose?
That's going to be basically
Why are we
I got the case.
it may get more clear when I give you the actual source.
Yeah, it lives in the case. I don't dare ever take it out.
I'm only going to do computations asymptotically far in the future, asymptotically late.
You get to bring
The actual strength
somebody like a wangle.
All right, so let's start this again. And I'm going to assume spherical symmetry. Throughout. That means I can write my mode. Let me label it by its energy here. So this is going to be a positive frequency mode. I can write it as usual in terms of a radial function that will, I have to designate an angular momentum eigen, quantum number here and the energy. So this is a function of r. And then I'll have the usual spherical harmonics, theta phi. And then I'll have e to the my. So basically, if you like, I'm solving the Klein-Gordon equation using separation of variables. And so I've written it in terms of a basis of spherical harmonics, Fourier modes in energy, and then, of course, the non-trivial bit is solving the radial equation. So let's look at the radial equation outside the shell. Okay, and I'm going to, for simplicity, take m equal to 0. So the mass, I'm going to set the mass of the scalar field to 0 here. And I'm going to have it minimally coupled. And then what you will find is that this equation is second order differential equation that has the following form. I'm writing it in terms of the torus coordinate. I will have the energy eigenvalue squared here. I'll have L plus 20. I will have the usual angular momentum term. Now, there are some terms here that, of course, are coming from the Schwarzschild background. You just have to work out what is the Klein-Gordon equation in this background. And you will have 1 minus 2m over r omega L. This is all equal to 0. But it's a linear second order equations that we can. And things simplify if I go far away, because far away r is large compared to this m. So these terms will be vanishing. This will reduce to 1. And I get a very simple, just the wave equation in the radial direction if I'm sufficiently far away. Okay, so I'm looking at an outgoing mode at Scri plus. I can write that. So it's a positive frequency mode. It is going to be just a plane wave mode. And a normalization is given here, and I have an e to the minus I omega t minus r star, right? This is an outgoing mode, which of course I can also write as an e to the minus I omega u, right? So when my outgoing modes are sufficiently far away, they are simply plane waves in the null u variable, right? So these are going to be my positive frequency modes in that I called UI modes there, and they're continuously labeled by the energy here, which of course is also is basically the radial momentum as well, right? Okay, now if you want an ingoing mode, similarly at Scri minus, that's clearly going to be something that we will call u twiddle omega prime is going to be v, right? Because an ingoing mode here is going to involve the combination t plus r star, right? So these are the modes that I want to whose overlap I want to calculate, but of course I have to do the propagation through. And now I need to do a little ask what happens near the horizon. Okay, now I have to do my patching through the shell, and I'm particularly interested in the patching that occurs here very close to the horizon, right? That's going to be where most of my effect comes from. So I claim that u minus u0 near the horizon should be minus e to the minus cu. Remember, this is basically saying that when I'm near the horizon, this is going to be, this is the Kruskal coordinate. Okay. So I'm assuming what goes into this, which I haven't said yet, but is that, of course, I'm asking that this shell have a large mass compared to the Planck mass, so that this patching here is happening in a nearly flat space-time here, right? And then I'm really simply thinking of this as, near this here, this is almost, so these Minkowski coordinates here are very close to being just the Kruskal coordinates of the black hole up there. Okay, so this requires that m, but this is what we want anyway, because otherwise the curvature is going to be too strong at the horizon. Okay? And so this allows us to, at least near the horizon, to write u as 1 over xc log u0 minus capital U. Okay? So this means that this function here, this mode, if I want to know what does it look like as a function of the variables inside the shell, I've got my answer here. This is the relationship. Now, inside the shell, we have that R, 2R actually, is capital V minus capital U plus 2R0. This is just a consequence of my definitions of the coordinates. This is just saying that the radial coordinate in Minkowski spacetime is just given by V minus U, and then we had the shift in by R0. So this tells me that I can actually immediately see that U must then be equal to V plus 2R capital R0 at. So this is going to be my reflection condition. So this tells me that when I get to this point, this tells me what is the value of capital V here. It's given by, I can solve for that.
There should be a minus before the log, right?
Possibly.
Yeah.
Yeah, probably. Let's say. Yes, thank you. All right.
Just to clarify, is the side here the surface gravity or the
Surface gravity, absolutely. Yeah, I guess I had introduced some other psi as well, but this is the surface gravity. We're just going back to our there was a reason why I inflicted on you all those coordinate changes at the beginning. So we're actually making use of that now. All right. So now it means we can write our mode, first of all, as a function of u, and then we can use this condition at the origin to tell us that we should replace u by v plus 2r0, right? And then we'll know what the mode is as a function of v going inside here. And the final step is to actually figure out what is the relationship between capital V and lowercase v, right? And so let's.
Could you explain this again why we also u minus u0 is equal to basically the capital U is the Kruskal coordinate compared to the little like the relation between the horizon in the horizon, then we suppose that u minus u0 is e to the minus basically.
Well, there are different ways to see it, but remember, when we did our Kruskal coordinates, we basically needed a coordinate that was well defined when we let u go to plus infinity, right? Because that the outside the lowercase coordinates they are there's a coordinate singularity at the and so and the way we did that was we went through these steps, and so you could say, okay, these are my, by definition, this was the definition of the Kruskal coordinate in there, okay? And then if your geometry is very close to being flat at the horizon, I can use this, I can basically say, okay, I will use then this coordinate and up to, I mean, there'll be some shift, of course, because, depending on where I am, and that's all I'm doing here, right? So the Kruskal coordinates are, if you look at the actual Kruskal coordinate system very close to the horizon, up to some trivial scalings by constants, they are simply, you look at the metric, it's given by, sure, there's a function of r out there, but close to the horizon, that r is just equal to rh, and so that's just a constant. So so the Kruskal metric, it really is the statement. This is kind of, I'm just stating the equivalence principle, if you like, that the space-time is locally flat. I can use Minkowski coordinates on there, and that is what the Kruskal coordinates are. And the relation then between the Kruskal coordinate and the outside coordinates is this. That was the construction we went through. And I mean, that's why we have c here and not some other coefficient. That was precisely the construction that gave you a non-singular coordinate system at the horizon. Okay? So, and then what we're going to do is we're going to view the outgoing mode as a reflection of an ingoing mode here. You could say, for example, if we impose Dirichlet boundary condition on the scalar field at r equal to 0, then we'll find that our original mode, which we now have some slightly complicated function of u, will now just get to replace u by this at r equal to 0. So that means I now have a function of capital V. And the final step so I'm going to view outgoing mode as a reflection of an ingoing mode. And so I'll write my u mode is therefore 1 over 4 pi omega e to the minus I omega. And now I have to yes, it'll be a plus divided by xi log u0 minus 2r. These are just constants minus capital V, right? So this is the outgoing mode written in terms of the V coordinate using these matching conditions that we've given you. So now the final step is, again, we're going to use that we have a large mass shell, and now we're doing a matching somewhere far away, and that's, again, will just be, I can really, so I have some coordinate here, V, capital V here, so this is the point where I'm doing the matching. Now, both of these coordinates, if I have a large shell, these are just different coordinates of the local Minkowski spacetime, right? Asymptotically Minkowski spacetime. So at best, they're going to be shifted by some constant. And it turns out that constant value doesn't really, isn't really going to be all that important for me. So assuming spacetime curvature is small outside horizon, or in this case, outside the shell, capital V can just be written as V plus some constant. And this function, u omega, sorry, so I have to specify now. It's going to be this function here, e to the minus I, sorry, plus omega over c log. And if you think about it, it's just going to be b minus v, right? Because this is going to be some constant that I shift by, but then I had decided that I was going to make my, whatever that collection of constants that I'm now left with, u0 minus 2r0 plus this guy, I'm going to call them capital B, right? And so this is going to be my final expression. This is if v is less than b, and then it's simply 0 if v is larger than b, because anything that would have come from up here would have to have reflected inside the black hole, and causality tells us it cannot have come back from up there. So there will be no support there. Okay? And now let's check, is this really what is the, we're assuming this space-time curvature is small outside the shell, and we're only looking at the shell when it's still outside its own Schwarzschild radius. So let's just do a little check here. Let's calculate mu nu lambda sigma. This is called the Kretschmann scalar for Schwarzschild. Black hole. It has this value. It's an easy calculation, tells you it goes like 48 m squared over r to the 6. And so that'll go to 3/3 m to the 4 as r goes to m. And so that's clearly, for a large black hole, is going to be a tiny number. In fact, if you calculate it at the, for a Schwarzschild black hole, this gives you something like, well, depends, of course, on the mass, but we're assuming this is large in the units we're using, so this is small. And then what we're interested in is doing this matching along here, and that's actually, here r is always going to be bigger because the shell is coming in, right? So this is only going to be smaller. This is as big as it gets, and that's a tiny number at the horizon. So these assumptions I'm making about the patching through here being in close to flat spacetime are well justified if the black hole is parametrically large compared to the Planck scale. All right, so now we can do the Euler integral. All right, so let's do that. Okay. So we're going to take an ingoing mode at scry minus, which we had written earlier. Maybe I've erased it already. Nope, here it is. So that's the thing we want to calculate. So beta omega omega prime then is going to be minus u twiddle omega prime, inner product with u omega star, right? That was the definition. And that's going to be, now remember this guy involved two terms. One where I took and had a derivative on this. So I'm integrating along my Cauchy surface, and in the limit that I'm going at very early times, that reduces to an integral over the v. So we're basically taking a slice that's very much close to here, right? Okay. So I'm going to integrate v from minus infinity to plus infinity. Well, actually only to 0 because one of these guys only has, sorry, to b, because one of them only has support up there. And it involved two terms. It had, I can have, it's on one hand, it's the integral of this guy times the derivative of this, and then minus the opposite. And then I'm going to do an integration by parts to have the derivative acting always on this guy, which is simple, right? So let's do that. So I'm going to get twice. So when my integration by parts is going to switch this guy upstairs. I'll have minus infinity to b dv. I will have an e to the minus I omega prime v, and I will have a b minus v to the power I omega over c, right? I've exponentiated the log here. All right. And then comes an exercise for you guys. We can talk about it, how we do it, in the discussion session this afternoon. It's a little bit of, you have to do some massaging, you have to do some, but you end up with the following answer for this integral. You get a phase factor, which I'm not going to write out here. You end up with omega prime downstairs. You then have an e to the minus pi omega over 2xc times a gamma function of 1 plus I omega over c. Right. So leave it as an exercise how to get there, but you can sort of see what you're doing. You're going to change variables. You're going to rescale out the b here. You're going to get b to some I. So that's part of your phase factor here. And so on and so forth. You then want to turn this into a gamma function, so you do that by, you have to rotate your integration contour, and that actually tells you why you have this factor. So let's not dwell on that right now. This is the answer that you will get. And then we need to take its absolute value. And the reason we're not worrying about the phase factor is because it's going to go away in the next step. Yes?
If we are asserting that big V is equal to small v plus a constant, how is it that we can match like big V is equal to small v is equal to 0 at the origin?
No, that's just where we figured our. You should have asked that a moment ago, just before now I've erased it. I picked an arbitrary place on the shell, but if you notice, I was always very careful not to have it coincide with the reflection back. If I pick another place on the shell, it just means I'll change the value of b. But at the end of the day, b actually only appears inside this phase factor that you get at the end. So all the b dependencies in here, and that is actually going to go away right now. And that's as it should be, because the value of b is just a question of where we put the origin of our coordinates. So we had better not find things depending on it. Okay, so what we will find then is that this is the thing I'm interested in. is therefore going to be 4 e to the minus pi omega over c divided by omega omega prime, and then I omega over c all squared. And then there's another exercise for you. Use some gamma function identities. This will tell you that this is 8 pi over c omega prime, 1 over, amazingly enough, 2 pi omega over c minus 1. Okay? And you notice this, of course, is exactly the hallmark of a thermal spectrum. This is e to the minus e over kt. Sorry, e to the e over kt here, and the temperature is precisely c over 2 pi, right? And omega is the energy. So there you have it. You get a thermal spectrum. Okay? Now, there are some notes to add here. When you plug in the numbers, I mentioned this before, you get 6 times 10 to the, well, maybe I didn't do it until now. So Kelvin, m. So if you're doing this for a solar mass black hole, you get this 10 to the minus, so it's roughly 10 to the minus 7 Kelvin. So, 0.1 microkelvin if you have a solar mass black hole. So the real black holes that we know about out there, they're not very warm. Okay, so that's one thing. Another observation is that, well, in order to get the answer, the final answer, we actually have to integrate over all the contribution, all the possible modes early on, right? We want to know what is the occupation number of a particular mode. And that's going to give us a logarithmically divergent answer. So, what's going on? Well, of course, we knew this is going to be a little bit of a funny thing because we've assumed that the black hole forms and then just stays there forever, right, in this calculation. So we shouldn't be surprised that we're getting a divergent answer at the end because, well, we're allowing it to radiate forever. So what you need then is to take into account the back reaction. And the black hole actually evaporates. Okay? And this we can systematically include in a two-dimensional toy model, which I hope to show you tomorrow, how that works. Okay? In 4 dimensions, we actually don't know how to do that. There, what people do is simply kind of put it in by hand. They take this result and they say, well, the evaporation is a very slow process. So at any given time, you can take this and you just let Xi evolve with as the black hole loses mass. We'll lose control of the effect, of course, when Xi is going to infinity at the very end. Temperature is becoming very hot, but for most of the history of the black hole, this is well under control. And then you simply cut off your story at that point. Okay. So this is not a divergence that people worry about so much. Okay. Now, another worry was the one that I alluded earlier, is that the dominant contribution to this overlap integral is comes from very close to the horizon. It comes from U goes to infinity region. So it's extremely close to the horizon. And this is something that we do need to worry about, perhaps. And that, because that implies that at intermediate steps in the, when we're actually calculating these mode solutions, we've actually tracked them back along the horizon, the infinite, you get well, actually in the limit that u really goes to infinity, we're doing actually an infinite blue shift. So these are arbitrarily high energy modes when they set out from the, so that's formally what's going on in the calculation. So it was an important, so this was called the Trans-Planckian problem. It arises also when people are doing, when they're doing early universe cosmology, inflationary models. You have similar problems. You have modes that are sort of formally are coming from sort of, so you would want to somehow introduce a cutoff on this. And then you might worry if you put a cutoff that you just simply lose the whole effect. And this was a concern that maybe this effect was just a fiction of having ignored this problem. But I think a very convincing demonstration was done by Corley and Jacobson. I'm not going to go into it here, but it's a rather nice calculation. This is actually addressed by doing the calculation very differently. You regulate your Trans-Planckian mode. You basically, you have an infalling lattice. And this is Corley and Jacobson. And this would have been 1997. Okay. So they're infalling, they choose coordinates which are called infalling Painlevé-Goldstrand coordinates. They're basically coordinates where your time variable is the proper time of an infalling observer in free fall. And then they said, well, we will then in this model, we will regulate we will not allow Trans-Planckian. We'll put in a cutoff that is slightly above the Planck scale and study the behavior of this model. And then what they found was that they actually were able to calculate an outgoing spectrum, which was exactly Hawking's spectrum. It looks, the origins are extremely different in this model. It's actually what's happening is that your lattice is moving now, of course, through an environment where you have, it's a curved environment. The background metric is changing as you move in. So the dispersion relation of your lattice model is actually gradually changing. And when that happens, you have what's called mode conversion. So there was also an overlap integral to do there. And they ended up with the same spectrum, considerably more complicated computation than what Hawking did, and manifestly no Trans-Planckian modes by construction. Okay, so that tells us that this is also a problem that we don't need to worry so much about. Okay. Now, we are missing some pieces of the story here that I'm not really going to go into. There is, of course, a correction to this spectrum. Which is due to mode propagation outside. So basically, when we're in this, we just assumed that the mode would just travel freely. What will happen is, of course, there will be some backscattering due to the background curvature. We dropped all those R-dependent terms, right? When we looked at our modes, well, the R-dependent terms, they're there when you get closer to the horizon, and what you have to think about is there's actually a potential that these modes are propagating in, and there are, you have to calculate reflection coefficients and transmission coefficients of that potential. Those things are called gray body factors. They They modify, you still get an approximately thermal spectrum, but it's slightly modified, but in a way that is computable. I'm just not going to go into it here. So due to more propagation in Schwarzschild geometry. So outside black hole. So these are usually referred to as gray body factors. So they're an important part of, if you actually want to get the answer here. Now, I really, as I said before, I really recommend, if you're interested in the subject, to take a look at Hawking's original paper. It is very clearly, it's you know, for additional issues that need to be of this original calculation. For example, there's one thing you may have noticed. I completely sidestepped the issue of what happens to things that go into the black hole. They were simply not needed for this answer. But Hawking does discuss that in his paper, and that is also, of course, what led him then, shortly afterwards, to pose his famous information paradox, because that has to do with the stuff that goes into the black hole. All right. Now, there is a closely related set of calculations that one can do that don't, strictly speaking, not have to do with the information paradox, but I think I want to mention them here. And that is, you can do computations on static backgrounds. I alluded to this earlier, that this Hawking effect, it's a very low temperature effect. Things are going to happen very slowly. So for many purposes, it's useful to just think about the eternal black hole background, where things are more simple because we don't have an evolving situation. We just have the maximally extended Schwarzschild spacetime, or ADS Schwarzschild, you know, depending on what we're looking at. And so doing quantum field theory on that is actually a way to learn a lot also about black hole thermodynamics. I will not really do that much here. I will come back to it just a little bit when I do the Unruh effect. So if I have a maximally extended, possibly ADS Schwarzschild black hole. So this is also what we call an eternal black hole. So first of all, this gives us an elegant mathematical formulation. Secondly, an important feature here is that the results you get, they depend on the choice of vacuum. That actually amounts to a choice of coordinates. When you say a choice of vacuum, you mean what do I designate as positive frequency modes? What are modes that have negative frequency? And there are standard choices that people make in this business. There's what's called the Bowler vacuum. There's the Unruh vacuum. And there's the Hartle-Hawking vacuum. And the Bowler vacuum, you're actually just using your Schwarzschild coordinates to define your time evolution. That's something that is very natural when you're an asymptotic observer. But on a static background, what you will find is that you can now calculate the stress tensor of your scalar field in this background. And if you use this, if you normal order your stress tensor with respect to the Schwarzschild time, you get an answer which is reasonable far away from the black hole, but it actually diverges at the horizon. And you would expect a strong back reaction to that. So you probably, this is not the vacuum you want to use as a starting point for doing some sort of semi-classical calculation where you include the back reaction. You can have now also, we have a different choice of coordinates. We could use the Kruskal coordinates, right? And that is what the Hartle-Hawking vacuum does. It uses Kruskal coordinates and it normal orders with respect to those. And then you will have good behavior on the horizon, both the past and the future horizon in this setup, and that actually formally will give you you have your quantum field state on the, let's say, the hour side of this. Remember, there is another asymptotic region. There's the left and the right. And so the quantum state on the right, when you go through this procedure, you end up, and we'll see, I'll do the analogous thing for the Unruh effect momentarily, or I guess in the next hour, but I will, so I will not elaborate on it here, but what you end up with is a thermal density matrix. So what the Hartle-Hawking vacuum seems to give you is a thermal state. And you would want to interpret that as a black hole in equilibrium with its some thermal bath, but as I mentioned, that is an unstable setup for asymptotically flat black holes. Possibly it's better behaved for, looks better for large ADS black holes, where so that the Hartle-Hawking vacuum for an ADS Schwarzschild solution is more meaningful, but it's actually still a little bit dubious what we're doing there. And then Unruh, in an attempt to actually kind of use the static configuration but still model the sort of thing that we were talking about, a configuration that has a future event horizon but no past event horizon. He arranged his choice of vacuum so that the stress tensor was well behaved on the future horizon, didn't really have to say much about the past horizon, and that's another interesting vacuum choice to study. But I'm going to, I think, stop here now. So this is all I'm going to say about the Hawking effect per se. What we've achieved is to see that we get a thermal spectrum. The next lecture I will be about a very closely related effect, which is the Unruh effect, which actually takes place in flat Minkowski space-time, but it's an observer who's not an inertial observer. It's a uniformly accelerated observer. We will find that we get a very similar looking result. I'm not going to repeat the exact steps. You can actually do that computation using this method. I'm going to show you another method, which is the one that Unruh used. Yes?
I would like to see that from that expression of beta, that this is 0 for fast space, and I think we can get it from the limit psi equal to 0, right? Because for fast space, the surface gravity should be 0, if I'm not wrong.
The flat space limit of this computation is actually a rather singular one, because you're thinking about making the black hole smaller and smaller. But that's actually a singular limit because the Hawking temperature is blowing up on you there. So you can't really do that. So.
And another thing, also I think I've heard that we have also a Banks Davis vacuum, maybe it's cosmology.
That's in cosmology. And that's the analog of the Hartle-Hawking vacuum, if I remember correctly. Right. It's I think that's the one where your past horizon there is, yes, it's the analog of Hartle-Hawking. Yeah. All right, so we will continue this tomorrow. But I guess